Great, thanks. So we just talked about using graphs to analyze data, and my talk is focused on going beyond graphs towards things like simplicial, hyper, and relational structures. It came up in a great question by Stefan about the package dependency graph, right, isn't a graph on packages. It has these extra things, these versions playing a role, right? I'm motivated here by this idea that whenever we're doing graph analytics, there's always more structure than just the graph. That can be like this version structure and the dates, like in this package dependency modeling. It can also be things like dynamical systems. So you have a multi-agent network, you have a communication graph of what agent can talk to what, but then those agents are doing something physical. So there's always additional structure beyond the graph, and I want to get into that. So Algebraic Julia is an ecosystem of packages, and it has a fairly large team behind it. Here are some headshots of people who've worked on various algebraic Julia packages. I'm currently getting notifications from my students who are watching the live stream. So I don't know how to turn on Do Not Disturb here. Focus? Yeah. I don't need the live commentary from you. I'll leave the student nameless. Okay, so ACsets. So ACsets are a data model that generalizes graphs. So it stands for attributed C-sets. This is a pun on G-sets, which are group actions. C-sets are category actions. So totally weirdo name, but we like it. And so they are an in-memory implementation of a categorical model of relational databases. And each database schema can often form the backbone of a algebraic Julia package. So some are combinatorial spaces, which represents things like simplicial sets, which are used in topological data analysis and computational physics, or Petri nets. We have a package, algebraic Petri, which does like process modeling for like concurrent processes, and you could use that for verification and validation of distributed processes. So here's an example, and I was talking with some GraphBlaws people here today at lunch, and we're talking about like, what do the numbers when you have weighted graphs, what do the weights mean, right? So there's always more structure. Whenever you have a graph, there's always more structure. And so something like a roadmap, right? You think of a roadmap, and if you're a network science person, you might pitch roadmaps as their graphs. Well, but also the edges have lengths that are the lengths of the road segments. And also the vertices have coordinates, the x and y coordinates. And like, oh, but the lengths should really correspond to the difference between the points, right? And so now a road network is not a graph, it's a relational database. So you have like an E table. Well, I should first start with the V table. The V table is for vertices. The E table is for edges. Then you have some type that's going to play the role of numbers here. And every edge has a source vertex and a target vertex. Every edge has a length. Every vertex has an x coordinate and a y coordinate, right? And so this is the relational database schema for how to store a road network. I said that, but road networks are actually more complicated. Edges are not, they're not by length, they're like a whole geometric curve, right? So the more you dig into any modeling activity where you're using graphs to model something, the richer the structure you'll find. Cool. And so we have in Algebraic Julia, we have a little DSL for specifying these schemas, and then automatically generating all of the Julia types necessary to represent databases over the schema. And so all of that's automated. I think a lot of the reason why people don't do these custom data structures for their problem, and they try to fit everything into a graph or fit everything into a matrix, is like, I don't want to do all the work of implementing a whole graph theory library just to do like my special type of graph. So I'll just do like graphs with arbitrary metadata, and then trying to use them, like, I'll show more examples of this later. It's kind of complicated. So ACsets have two perspectives. One is just as data structures. You have a domain-specific language for specifying the schema, and all of the implementation is automatically generated from that specification. It covers anything that's like a graph, so any kind of network science-y type thing. We call them combinatorial structures. They come with efficient indexing and reverse lookup, so that they have a generalization of the adjacency matrix, of the like sparse adjacency matrix that they can use. They have serialization and deserialization, all auto-generated for you. And you can convert between them with a package we have called data migrations that lets you do things like take a road network and forget the embedding and the lengths and get a graph, right? So automation, not only automation of the individual implementation, but also automation of the conversion between different schemas is really important to make this work. Then ACsets also live in a category. So you don't just have a set of databases over a schema, you have a whole mathematical structure called category, and it has really cool things that let you do things like compare instances. So just like graph homomorphisms let you compare graphs, talk about subgraphs, stuff like that. For every schema, there's a notion of homomorphism between database instances. I'll show you a little bit here. Yeah, so that notion of morphism allows you to imbue every such category with a logic. So you can think of, you have a domain of discourse, which here is a graph, G, and you can pick sub-objects. We'll pick two sub-objects, A and B. So the part that's highlighted in blue is the sub-graph that this proposition refers to. So A is this part, and then B is this loop, and these guys over here. And then you have logical connectives like and or. So and plays the role of intersection, or plays the role of union. You have things like complements and subtraction, so you can do A minus B. You have negation and double negation. And then you have operations like expansion operators, expansion and contraction. And these logical primitives let you write generalizations of graph algorithms. So for example, the not operator always does the notion of induced subgraph. So if you start with a notion of subgraph and you want to find the induced subgraph that corresponds to that graph, to like those vertices, you can like double negate. And that will work not just in graphs, but it will work in like road networks, simplicial complexes, hypergraphs. Any combinatorial structure has a notion of an induced subobject, and this logic lets you define that in a schema-independent way. And then the expansion operator lets you define things like breadth first search in a schema-independent way. So it always grows your subobject by kind of one layer of additional data. Okay. So another example is simplicial sets. Simplicial sets have become very popular for topological data analysis. And simplicial sets are to simplicial complexes the way directed multigraphs are to simple graphs, right? So they're directed and they allow multiple edges. And so what are they? Well, you have a table of vertices, you have a table of edges, and a table of triangles. This is for a two-dimensional simplicial complex, or simplicial set. Every edge has two vertices, every triangle has three edges. And then there are things like the simplicial identities down here, which tell you that the edges on a triangle, the three edges involved in a triangle, need to form a triangle. So the target of the first edge needs to be the source of the second, and the target of the second needs to be the source so that it makes a triangle, right? So here's the definition of an embedded delta set, and we use these for computational physics, where we need to have them embedded into Euclidean space, and we need them to be oriented so that we can talk about signs, stuff like that. So yeah, once you define this schema, you generate data structures, and they will store these combinatorial structures like this. Okay. Yeah, so why do I care about simplicial complexes? Because we're going to use them in computational physics. And then, of course, they're very popular in TDA, topological data analysis. And this is all based on the idea of the face poset of a graph. So if you start with a graph, you can look at its face poset. So it's vertices and then edges, and each edge has two vertices. That generalizes to the simplicial complex, where now you want to store the triangles in this complex. And now your triangles have three edges, right? So this is a thing that extends to arbitrary dimensions. And on top of simplicial complexes, we've implemented something called the discrete exterior calculus, which is a mathematical modeling framework for computational physics that treats the geometry of smooth manifolds as a first-class citizen. So you're not just doing physics in Euclidean space with coordinates. You're thinking directly in a coordinate-free manner about manifolds and physics on manifolds. And then you can think there's a smooth exterior calculus for the continuum, for like Riemannian manifolds, and then there's a discrete exterior calculus, which is algebraically equivalent for simplicial complexes. And based on this discrete exterior calculus implemented on simplicial sets, we have a computational physics language. So here we're using another DSL, also implemented in Julia, to specify a porous convection model. So here we have variables, we have operators, we have equations. This little DSL is describing a computational physics thing. And I wanted to show results. You can't put animations in Beamer. So let me do entire screen. I might regret that decision. So the resulting physics is here in the Decapodes documentation page. This little snippet of code up here. So here's where the physics are being defined. It generates this hypergraph of, this is the computation graph of the physical equations, which again, a rich graph structure with a lot more going on than just vertices and edges. Right? So we have this rich graph structure. Then you make the mesh, which is a simplicial complex, and you can simulate. It uses the SciML simulation stack, so all the time stepping is done by SciML here. Right? And it doesn't really matter what physics that is. It's just cool. Okay. And then I want to put this back into slideshow mode. Okay, cool. So yeah, so these decapodes are they're a system of sparse matrices. Each operator in this, it's actually like a hypergraph of sparse tensors in order to define these physics. Okay, so let's talk about hypergraphs. So hypergraphs are used in numerical computation at the frontiers of things like tensor networks. So you can imagine these being tensors, either like multidimensional arrays, either sparse or dense. And so each bubble is a multidimensional array. Each vertex is an axis of one of those arrays. And what it means for when two systems are connected to the same vertex is that you're going to do a tensor contraction. And thus, this tensor network corresponds to this tensor contraction, where you're summing over these triple products here. In order to implement things like that work with hypergraphs, we actually use a thing called undirected wiring diagrams. These are hypergraphs with boundaries. So you have your subsystems, they interact with variables, and then there's this extra boundary on the outside of the like variables that are exposed to the outer world. And so this undirected wiring diagram framework lets you build hierarchical systems because you can like do a tensor contraction with the result that is a tensor, and then plug that into another tensor contraction, right? And what's cool about this is like these little diagrams are combinatorial structures. There's a finite number of boxes, a finite number of vertices, a finite number of wires, and so they can be arranged into an hatchet here and stored as a relational database. What I've noticed in the literature is there's a lot of times when people have little variations on a theme, right? They want to do, like my road network example. It's a graph with edge weights and vertex coordinates and stuff like that. And so the PetreNet literature, if you use PetreNets to model concurrent processes, is like all over the place in PetreNets. Everybody's got their own little custom version of PetreNets. And so they have things like species, which are the circles, transitions, which are the boxes, and then input and output arcs connecting them. These are directed multi-hypergraphs, if you want to think about them that way. They're directed multi-hypergraphs. But then you want to like put there's something called the token game, which is how you use PetreNets to model concurrent systems. You put tokens on the states, and what the transitions do are they move tokens around, right? So it's like, okay, well, I also have tokens, and every token is in a species or a state. Okay, but like sometimes the tokens are different colors because they're different kinds of resources. So I have all my tokens are going to have colors from some type here. Okay, so now I have colored tokens. And then it's like, okay, I want to use this as a model of these processes happen at different rates. So every transition is going to have a rate at which it occurs. So now this would be like a PetreNet with typed tokens and quantitative rates, right? You don't want to re-implement a whole library around that, because this would require, like, the normal way of doing this, you'd either pick the richest data structure you have, implement that, and then say, well, if you don't want tokens, don't put any tokens in, right? If you don't want rates, set all the rates to 0. If you don't want tokens to have colors, just make them all the same color, right? So you'd either go the most general implementation and find all the other implementations as special cases. Or you'd write 4 pieces of software. You'd write a PetreNet library, a PetreNet with tokens library, a PetreNet with type tokens library, and a PetreNet with type tokens and rates library. Neither of those are good. The people who don't care about token colors don't want to always be setting the token colors the same, and they're going to have bugs and stuff like that because the software is not fit for their purpose. So anyway, this ACsets perspective lets you define the schemas and automatically generate the right data structures. And so that lets you really develop the goal of this whole framework is to let you develop software using the right abstractions so that your data structures are always matched to your application as tightly as possible. And of course, we want to go beyond. Part of the reason linear algebra is so dominant, right? Like it's so useful, and everything goes through matrix, right? Everything goes through matrices. We're Julia programmers. We want to write generic code that is also optimal. So let's do that, right? Okay. Can I get a time check? I saw somebody holding signs up.
About like 13 minutes.
I have 13 minutes? Okay, I have plenty of time then. Okay, great. So Clique trees is a new package that's been released and integrated into a variety of other packages. It is for doing tree decompositions, which are a technique for accelerating sparse computations across a wide variety of fields. So I'll talk a little bit about Clique trees and its performance. So what are tree decompositions? If you start with a graph, you want to decompose it into a collection of subgraphs so that the connectivity information is preserved. And then, like, why do we care about tree decompositions? They show up in algorithms like sparse Cholesky, where the sparsity pattern of the Cholesky factors will depend on a chordal completion of the graph, which is the chordal completion is what you need to compute the tree decomposition, right? So I keep hitting that. So these tree decompositions are deeply connected to how sparsity patterns change in sparse linear algebra. And then they're also used for things like probabilistic inference, tensor contraction, sparse optimization problems. And they're deeply connected to the theory of fixed parameter tractable algorithms. So there's a class of algorithms that your thing is NP complete, so it's intractable in general. But if your input is structured in a specific way, you can build algorithms that are polynomial in the size of the problem, and then all the exponential time is in the structure parameter. So if a graph has low tree width, which means it has a good tree decomposition, then FPT algorithms will be feasible here. Okay. And then, yeah, tree decompositions are not new. They've been known since like sparse Gaussian elimination and sparse Cholesky for a long time. So Clique trees encodes and decodes tree decompositions from vertex orders. So every vertex order induces a tree decomposition. So that's why like matrix reordering techniques, like those from sweet sparse. So matrix reordering and graph partitioning are deeply connected, and it's through this encoding and decoding of tree decompositions as vertex orderings. Yeah, and so Clique trees can, given a graph, compute an efficient tree decomposition. You start, in order to do this process, you start with elimination orderings. This is really coming from the sparse Cholesky world, right? What's the right way to reorder my matrix so that when I run Cholesky decomposition, I minimize the fill. So you take anything that can produce a elimination ordering, like approximate minimum degree or METIS can both produce these things, and you start with any elimination ordering, and you can build a tree decomposition from it. So Clique trees has already been integrated with the following libraries, or at least most of these following libraries, for probabilistic inference, Bayes nets, or Scruff, tensor contraction. There's a few options here, and then same with semi-definite programming, combinatorial optimization, and quantum computing. These all rely on fixed parameter tractable algorithms that are using tree decompositions. And so you can schedule a tensor network contraction to minimize the width of the decomposition, which bounds the time complexity. And you want to minimize the separator width, which controls the space complexity. And these are properties of exploiting the tree decomposition. It's exactly like matrix factorization, where you're trying to solve a linear system. You do a sparse LU or a sparse Cholesky to build some to reorder the matrix and build the factorization, and then you use the factorization to solve systems. The corresponding version of that for tensor networks is you first schedule the tensor contraction, and then you have to exploit that schedule. You have to execute that schedule. So time complexity and space complexity are measures of exploiting the schedule. And then here we're going to call running time is what we're going to call the time it takes to compute the schedule, right? So you want to build you want to run the fastest, which means minimizing the width. You want to use the least amount of memory when you execute the schedule. That's the separator width. And you want to have the fastest running time so you can compute the schedules quickly. Okay. And then this has been deployed in existing tensor network algorithms or packages. Okay. And so, yeah, it's integrated with both Ka-Hyper, which is a hypergraph partitioning library, and METIS, which is kind of the gold standard. So these are benchmark plots. The x-axis is our time, the y-axis is their time, and this is the time complexity of executing the contraction. So everything above the line is performance improvement. Everything below the diagonal is performance regression. So we're generally producing higher quality time complexities, generally producing higher quality space complexities. So more of the points are above the diagonal, right? So more than half the time we're winning for space complexity. And then for running time, when we use Ka-Hyper, so the same scheduling, the same vertex reordering backend, right? It's like win 2/3 of the time. When you use METIS, you win 100% of the time. But METIS is faster than Ka-Hyper. So that's to be expected. Yeah. So there's a little bit of innovation here in using existing data reduction techniques to pre-process the graph. This is all about shrinking the graph. So there's a couple of different operations you can do. You can exploit something called twin classes. So if two vertices have the same neighborhood, you can treat them as if they're the same vertex. here the red vertices are being merged and the blue vertices are being merged. And then there are rules here that are like, if you have a vertex that's connected to the graph with only 2 edges, you can clip this vertex off. And then again, now you find 4, clip it off, 1, clip it off. And these let you reduce the graph dramatically. And Clique trees alternates these 2 strategies. It does this twin width, yeah? Oh, that was 5 minutes left, thank you. Okay, so it does the twin, it finds the twin classes and merges them, and then it applies these rules to clip vertices off. And both of those techniques, by like mixing and matching those techniques and iterating them, you're able to produce very small graphs that you then give to metas, right? So a lot of this performance is shrinking the input size using these rules, using a state-of-the-art scheduler, and then like reinterpreting what sequence of rules you did to get the right answer. Okay. Yeah, so our high-level conclusions here is that I think whenever we're thinking about sparse data or network science or any application where we're modeling with graphs, we should be open to thinking about higher level structures, right? Either richer structure, where we're including quantitative information and we're seriously modeling. The points are embedded, the edges have length, like really take that stuff seriously. Or richer structures like simplicial complexes and hypergraphs, where you have multi-arity relationships. And then ACsets will help you do that in software. And then Clique trees will allow you to partition these, like by partitioning graphs, build these tree decompositions. We already have worked out theoretically how to use tree decompositions for arbitrary combinatorial structures. And so that's the future work, is to use Clique trees on ACsets so that we can build tree decompositions of simplicial complexes or tree decompositions of hypergraphs, or whatever rich data format you have, like PtreeNets or whatever you're working on. And that will open the door to parallelism in these combinatorial algorithms. So I think that's on our roadmap, and stay tuned for more development there. Thanks, and I'll take any questions. I'll also show the bonus slides to the stream. Here's how you do semi-definite programming. You rewrite it using chordal decompositions, and that's built into these other libraries. And it's built into JUMP. So the easiest entry point might be using this JUMP module, math opt chordal decompositions. Great.
So are there any questions from the audience?
Yeah.
Do you have any, so this talk is about like abstract composable data structures for stuff like statistical complexes.
Mm-hmm.
So are there any built-in methods for like homotopy estimation and stuff like that?
Yeah.
Repeat the question for the mic.
Oh, yeah. So the question is, like, when you're working with abstract simplicial complexes, are there built-in methods for homotopy stuff? No. The application layer, so the thing we can automate is just like the data structures and like basic manipulation of the data structures. The application layer, like once you have simplicial complexes, you want to compute homotopy or something like that. You still have to write the application, yeah. For now. Soon you'll be able to ask Claude, can you write me a Julia package for computing homotopy groups of arbitrary abstract simplicial complexes? Yeah.
Have you mentioned knowledge graphs?
Oh, knowledge graphs are awesome. Yeah. So, so this categorical perspective on on databases, there's something called the growth and deconstruction, which takes an arbitrary relational schema and computes, well, it takes a relational database and computes the knowledge graph that is equivalent. So you can, basically the way it works is it takes your database and it blows it to smithereens by it makes a graph where each vertex came from a row in your database and each edge came from a field in the database. And so this growth and deconstruction will like explode your database into a knowledge graph, which is a graph with types. Like the vertices have types and the edges have types. And so that is implemented. So if you have knowledge graph, like algorithms for knowledge graphs, you can use them on, like you can integrate them into this framework. Great, thank you so much.